that requires a computer, and I'm not comfortable doing take-home tests for a class size of 185 million. Whatever. All right, so I just doubled it every time. It helps you see changes more rapidly. And all I'm doing is I'm pasting in the values. So these aren't formulas anymore. If I change something on the other cell, these don't change, right? And that's the whole point, because I am changing something. I'm changing theta I. But none of these values are changing as I'm changing them. And so now I get, as you can see, I have a couple of rows here. And again, I'm going to make a plot. We'll do dots here just because we have so few.
How do you separate the data out?
I just make one where they're combined and then I delete one from each. Okay, so what happens to the conversion? It's decreasing, right, the whole way through. And this confirms what Solver told us. If I want to maximize the conversion leaving a 500-liter reactor, don't feed any inerts. And then what's happening to the temperature, as I put more and more inert in, the temperature leaving the reactor gets higher and higher. And again, that's what we expected. It's compensating for some of that. It's giving up some of its heat to keep the reaction happening at a higher temperature. So there's just more stuff to cool down, in other words. The reaction is cooling down stuff, and now there's more stuff to cool down. Okay, the problem then goes on, but before the problem goes on, would we expect a similar, what's going to determine whether or not there's a maximum here for the conversion as a function of the amount of inert I flow in?
The rate law? Reaction.
That's part of it. The reaction energy is part of it. But in what way? So if I decrease the reaction energy for this problem, will I get a maximum? Or do I need to increase the reaction energy so that a maximum shows up on that curve? Why? Well, let's take an extreme example. You say maybe decrease it. Well, what if I make it 0? Then what happens as I increase the amount of inert? Does the conversion go up or down?
No, it's down.
Down. No, the conversion is going to go down, right? So there's not going to be a maximum. I'm not going to ever increase conversion if the delta H of reaction is 0. Because the whole point of the inert is that it's helping mitigate the negative effects of an endothermic delta H of reaction. So making it no longer endothermic is not going to help. So the downside of this approach of me not setting up 15 different spreadsheets is I can't come over here and change delta H, and then these plots are not going to update, right? Because these are just values. So we'll just do another one real quick. Let's see what happens if I double this. Didn't help, right? It's still decreasing monotonically. All right, so look at the rest of the problem. I think it's going to ask us to switch this to an exothermic reaction. I want to double check. Okay, so there is not a maximum, is what we learned. So that's the answer to part C. Explain why. Well, in this case, as I dilute the feed, it's having a larger impact on the rate, meaning it's causing that the conversion leaving the reactor decreases more than its beneficial impact, which is that it keeps the temperature higher, which theoretically would lead to a higher conversion. But again, I can't just have it increase the temperature. It's also diluting my reagents, so there's no maximum. And then it says, what would change in parts B and C if the reactions were exothermic, and unfortunately it doesn't just leave it there, and reversible with a Kc equal to 2 at 1100 Kelvin. Okay, so how do I deal with the reversibility in my equation?
You just stop the Excel rows at the maximum conversion.
Do I have to do that? What's going to happen if I keep going? The conversion is just going to approach that value instead of 1, right? That's okay.
But you have to change
R. What's R?
Differential equation.
Little r, you mean?
Yeah.
Yeah. You got to think further back. Where did I get this from? This is based on a rate law, right? We wrote out rate was one of our steps. Design equation, rate law, stoichiometry. Well, the rate law was for an irreversible reaction, which is no longer the case. So we've got to redo our design equation. All right, that doesn't change. But now the rate equation is that it?
Well,
Minus. So this is now, we're going to put 1 for the little k to indicate that that's the forward rate constant. K, negative 1, concentration of B, concentration of C. Right? And so now, stoichiometry. Does anything change for the concentration of A as a function of conversion? No, right? It's just, that chapter is independent of the other stuff, right? It's just stoichiometry. It depends on things like gas phase, all that stuff. So this is the same thing that we had before, which was the concentration times 1 minus x T naught divided by all right, what's the concentration of B? Which is, by the way, conveniently equal to the concentration of C. So what's that?
We start with 0, right?
Yeah, there's none coming in with the feed. CA naught x times T naught. What about the denominator? It's the same. Remember that the denominator comes from the volumetric flow rate. It doesn't change. Okay, so now I go back to my rate law. And one other thing that I'm going to do with the rate law, does everybody have this? I want to erase it. No? I'll erase this then. So the rate law, it's not a big deal, but I don't have any information on k negative 1. But kc is equal to the forward rate constant divided by the reverse rate constant. So I can rewrite the reverse rate constant is equal to the forward divided by the equilibrium constant. And I'm going to substitute that in right here. The other thing I can do for simplicity, but we'll do that when we combine. But you could also just get rid of this and put a 2 there, because again, those concentration of B and C are the same. Okay, so let's recombine. I'll leave this one up here as a reference. So the rate equation is that. K, what's CA? That big thing, CA naught 1 minus X T naught divided by X1 XT minus the rate constant again, big equilibrium constant, and then concentration of B, which is that stuff over there, squared. Because concentration of B and concentration of C are the same. And we're not done. That's just the rate equation part of the design equation, which I erased.
I think you're missing a parentheses.
1 plus epsilon x, parentheses squared.
Yeah, thank you.
Not like that.
So in the actual design equation, it's this whole thing.
That's wrong again.
Yeah.
Yeah, I see. Thanks.